Okay, our topic for this week is energy use by appliances. It's fairly significant. Our appliance use, the main ones are the ones in our home. The big 6 or the big 7 are here. And that adds up to about 13 gigajoules of our household energy. So out of 600, it's a significant amount. So we'll do some calculations related to energy use with appliances. Now we have a device called a WhatsApp meter that you can plug into the wall and then plug into the appliance, and it'll actually track the energy used by the appliance. So this is a curve for my refrigerator at home. So you'll see, there's an energy spike here. It spikes up to, it's hard to see, but these are watts, so that's about 800 watts. So that's about 900 watts. So the power rating of the fridge, the maximum power that it draws, there's a brief spike there of current and power to the compressor, which is the only moving part in the fridge. Next, we're told that the fridge uses energy of 113 kilojoules over a time of 2358 seconds. So that's full cycle brings you up to here. And so you see that's, well, it's about 40 minutes. It's 2/3 of an hour. And then this energy, the computer was just calculating how much energy it was using as the compressor was running. Here the compressor kicked out and it was sort of in standby mode for a while, and then it started up again. This is just because, of course, thermal energy from the room leaks in and you need to run the compressor to keep the food cool. Okay, so power is a ratio of energy over time. And so we can find the power using these two numbers. Now, of course, this is going to be the average power, because as we just saw, the maximum power is 900. For this length of time, it really isn't drawing any significant power at all. So the number we've got here is an average. Let's work out what that is. So 113,000, we divide by 2358. So we get about 47.9 watts of average power. Now, if you look back on the previous page, you'll see a picture I took off a fridge. It says this one uses less energy than a 60-watt light bulb. And so that is indeed the case. The average power for this fridge is less than 60 watts. Now, next question is, how might this change over the course of the day or over the course of a year? Well, what might change, of course, is that the fridge might go off more often. Here, probably, it was just sitting on its own and undisturbed. As soon as you open the fridge door, of course, and close it, then this cycle will start when you open the fridge, usually. So that would affect the average power. So during the day when you're using it, the average power would be higher, but of course when you go to bed at night, you'll probably get back to this value. Something that might affect it is the temperature of the room. Right? So if the room temperature gets cooler, less thermal energy leaks into the fridge, the compressor runs less often, and this number would go down. Those are the sorts of considerations that would affect that value. So really, we're just saying power is energy over time, but we are recognizing there's a bit of complexity to that. The power actually changes over time. Here's another illustration of that, and this one gets into a little bit more into the concept of standby power. The standby power for that fridge compressor was almost nothing. But for other devices, say like a microwave, it is significant. Now you can't really say so on the graph, okay, because 1950 is the power that it draws when it's running. So here the microwave's on, it stops. There's some little bumps here when you open the door and the light bulb goes on. And here then is when the microwave's just standing there not doing anything. But it actually draws about 3 watts in that mode, mostly to run the clock. And over the course of a day, even though it's only 3 watts, that can really add up. So typical, we're not great microwave users in our household, so I monitored it for a week, and we used it about 45 seconds a day. So we're going to compare the standby power with the actual usage power, or usage energy, I should say, and standby energy. So for usage, it was on and drawing, well, first of all, I should remind everyone that power is an energy over a time. So an energy will be power times time. So the usage power was 1950 watts or joules per second, but it was only on 45 seconds a day. So we'll see how many joules of usage there was there. Now we use a lot. Oops, standby has a B in it. We use a lot less power on standby. It's 3 watts, but then it's on standby for a long time. There's 86,400 seconds in a day, and 45 seconds are usage, so the other 86,355 seconds are standby. So let's work out these two energies and compare them. That's the task in this example. So 1950 watts, we're on for 45 seconds, so that's 87,750 joules. 87,750 joules. Next, 86,400 seconds minus the 45 it's in use, so there's the standby time. And we multiply that by 3, 259,065. So you see, our microwave is actually using more power in standby mode by a factor of about 3. And so this, I'm sure you'll agree, is wasted because we really don't need that clock. So the appliance manufacturer should really have like a zero energy draw position where the microwave goes to sleep and draws, like a fraction of a watt when it's not in use. We don't need to power that clock all day, given that most of the time we're not even going to look at it. Don't know about you, but it's certainly not the main clock in my kitchen. Okay, so and this is not atypical. It's often the case that our usage energy and our standby energy, or rather, it's often the case that the standby energy is significant. Maybe not, more than the usage energy as it is in this case, but certainly significant, and therefore a target for reduction. There's a third example here, but we're going to do that one when we meet together in class. It shows a charging curve from the watts-up meter for my electric scooter. But more on that when we meet in class.